So hello, good evening friends. My name is Maikam Basumatari and I'm going to discuss today very important topic from my point group, that is the reducible and irreducible representation of carbon dioxide molecule. Okay, most, I mean, in some books it is not there and you will not find it in other sources also. Okay, it is very uncommon. So how we are going to represent is reducible and irreducible representation that I'm going to discuss now. Now you see here, first of all, that carbon dioxide is a linear molecule. What is this? Carbon dioxide is a linear molecule. Okay. So the structure of carbon dioxide is something like this. It is it is a linear molecule. So carbon dioxide, we have a linear molecule. Okay. And what you will see, that the point group of carbon dioxide molecule is d infinity h. Okay. So the point group of the carbon dioxide molecule is d infinity h. So if you see the character table of d infinity h, then it is quite complex one. Okay. So what we will follow is that for linear molecules, usually we can follow d2h character table. So for carbon dioxide molecule, we can follow the d2h character table instead of d infinity h. So here I have already drawn d2h character table. For d2h character table, this is the character table for d2h point group. So you can see here that these are all the symmetric operations. Okay. E for identity means was doing nothing, and C means the rotation. No, so C2 along z axis, C2y along y axis, rotation along y axis, and C2x, that means rotation along the x axis. And this I means what? This I means your center of inversion. Okay, center of inversion is a point where if we rotate the molecules, if you change the coordinates of the molecules, then you will find that the molecule will be similar. Okay, it is indistinguishable. Then if you see about this one, sigma actually it represents what? It represents your reflection. Okay, so this is a sigma along the xy plane. Along the xy plane, it means the reflection along the xy plane. Then we have the sigma along the xz plane, that means it is means what? The reflection along the xz plane. And we have sigma yz, that means reflection along the yz plane. Okay, and here we have h means what? The order. Okay, so order means what? Total how many symmetric elements are there, number of symmetric operations. So we have total 1 2 3 4 5 6 7 8. So here we have written order is equal to 8. So now we are going to see how we are going to represent its reducible representation for carbon dioxide molecule. From this character table, we are going to derive the reducible representation. Okay, from d2h character table. So you can see here that for reducible, we have just drawn here the simple diagram how you will represent the reducible representation for carbon dioxide molecule. That means what is here in character table, all these 8 operations you have to write here in similar manner. Okay, and this h means it is order. So you see now here, now in order to perform this operation, what you will have to understand, you will have to understand regarding the symmetric of the carbon dioxide molecules. So if you see the symmetric of the carbon dioxide molecules that I'm going to discuss here, you see that this is a carbon dioxide molecule, let us consider. Okay, and along this side, let us consider it is a z axis, no, and along this side we have x-axis, and this is your y-axis. So this is the carbon dioxide molecule. So you see here, in this, in order to find the reducible representation, you have to see here number of unshifted atom. Okay, that means how many number of unshifted atom will be there. We have to find this one through these operations. Then we will see the contribution per atom. Now what is contribution per atom? You can see here that I have written the contribution of certain characters. So you can see here the symmetric operation for E, identity will contribute 3. Okay, contribution of character of identity is 3. Then for inversion, it will contribute as -3, and for rotation it will contribute 2 cos theta plus 1, and for reflection it will contribute 1, and for improper rotation it will contribute 2 cos theta minus 1. So this contribution we will use in order to find this reducible representation of carbon dioxide molecule. So let us see the symmetric. Now let us symmetric of the carbon dioxide molecule. Okay, so if you perform this operation, now what is this number of unshifted atom? If you do e means what? E means nothing, doing nothing. Doing nothing means what? How many atoms are there in carbon dioxide molecules? There are 3 atoms, so number of unshifted atom will be 3 only. No, that means no atom has done any that means operation, so it is 3. So now we will see that C2Z. C2Z means what? C2Z means along this Z axis, what we are going to do is that along this Z axis we are going to rotate this carbon dioxide molecule. Okay, so if we hold this one along the Z axis and C2Z, am I right? So C2Z means what? 360 by 2, 360 by 2, which is equal to 180 degree. No, 180 degree rotation. So what we are going to do is that along this Z axis we will just rotate this molecule of carbon dioxide. So what you will find that this oxygen will come here and this oxygen will go there. No, so how many? So that means these two oxygens are moving from its position. So ultimately on number of unshifted atom we have in this case is only 1, because carbon will not move in that case. Okay, carbon will remain as it is, only the oxygen will get replaced. This oxygen will move this side and this will oxygen will move that side, so in 180 degree rotation. So what will happen, that carbon will is the only unshifted atoms. So we can write here that along this C2Z, the number of unshifted atom is only 1. Okay, so next what we will are going to see is that C2Y along the y-axis. So along the y-axis, similarly along this axis, if we try to rotate this carbon dioxide molecule, then you will see that this oxygen will come here and this oxygen will go there. So only this carbon is not moving from its place. It means only it is unshifted, but these two oxygen, they will interchange their places. So here also what you will see, that the two oxygen atoms, here also you are going to see that two oxygen atoms are replacing their positions. So here also unshifted atom along the z-axis, C2 along the z-axis is here also it is 1. Okay, that means only this carbon atom will be unshifted, oxygen will interchange its places. Then along the C2 z-axis, you see here C2x, along x what happens? Now you see here that this is along the x-axis. Okay, so if you try to rotate this molecule along this x-axis, okay, if you try to rotate 180 degree along this x-axis, then you will say that this will be rotating along 180 degree, this will also rotate 180 degree, and this will also rotate 180 degree along this x-axis. Okay, then what we will see, the none of the atom is shifting from its original position, it's just rotating. Okay, at the same position itself it is just rotating, so it is not shifting from shifting its position. Unlike from z, if we rotate, then oxygen will come here, this oxygen will go there. Okay, and along the y also, if we rotate, this oxygen will go there and this will come here. But along this x-axis, if we see, all the atoms are lying along the x-axis. So if we try to rotate 180 degree also, then we will not find any change in the atom or the configuration. Okay, the oxygen, this oxygen will remain in its own place, this also remain in its own place. So in this case, number of unshifted atom, so in this case number of unshifted atom will be 3 only. So 3. Okay, and this carbon dioxide molecule, if we see, it has only one center of inversion. Okay, this is the center of inversion, carbon itself is the center of inversion. So along any line along this any line drawn along this carbon will give you, when they are inverted in their coordinates, it will give you similar structure. So in this case also center of inversion we have 1. Okay, Now in order to understand this operation, that means reflection along x y and reflection along x z and reflection along y z. So in order to understand this one, let us see the uh, real this one planes. Okay, this has to be done in the plane, because sigma means what? Reflection operation. So you will see that we have already considered this is our carbon dioxide, and along this side we have z, and along this side we have x, and along this side we have y. Okay, so let us see this one. First of all, reflection along xy plane. So xy plane means what? This is x and this is y, am I right? So this is our xy plane. So we will just have to imagine, what we will have to imagine is that there is one mirror like, okay, there is one mirror that is passing through this. So this plane is nothing but a mirror, we will consider. Okay, so in this case what we will see, that all these three atoms, they are lying in the same plane, that means the xy plane. So ultimately what happens, there is number of unshifted atom will be 3. Okay, along the xy plane, number of unshifted atom will be 3, because they will not shift, they will not reflect anything. Now next operation is that sigma x set. Okay, so sigma x set, that means along the x set plane what will be the operation? Okay, how many unshifted atom we will get? X set. So whenever we, again let us draw, so this plane we have, this is xy plane. Okay, sigma xy we have done. Now similarly what we are going to do, so this is suppose your x and this is your z. Next operation is sigma x set. No, so sigma x set means what? It will lie in this position itself. Okay, so this is our sigma x set plan. Okay, sigma x set plan. And along this side, sorry, okay, and along this side we have y. You see, z means what? Z is at the top of the carbons. If we consider this is one here carbon, then here two oxygen, if we consider this is being double bond, Z is along the top. Okay, and x we have considered this side is x. So zx plane, so you will know that this whole axis is x and this is z. At the top it is z. Okay, this is z, and then mm, uh, this is x and this is z. Okay, at the top. So ultimately what you will see, that this plane is passing in this way. So from the top, okay, I cannot draw here very clearly, but this plane is actually passing from the top only around the x plane. Okay, so there is no any change. There is that means all the atoms are lying in the plane. Okay, so there is no any unshifted atoms. So I mean the unshifted atom is 3 in this case also. Now the next case is sigma yz plane. So if we again we will draw carbon, double bond oxygen, and double bond oxygen. Okay, and this is our z, and this is what? Y, and this is x. Okay, now so now we will see here that there is a plane, that means this is z and this is a y plane. No, so if you see clearly, this is a x z, z x y z plane. Okay, along the y direction it will go in this way. Okay, so that is your yz plane. So in this case what happens, you will see that this mirror is going cutting the carbon atom. Okay, in this way, and these oxygen atoms are in the that means this is a how will I be? So this is a carbon atom, okay. So this plane just cuts, and I have told you that this plane is nothing but a mirror. So ultimately what you will see that this oxygen will be reflected here in this mirror, and similarly this oxygen also will be reflected in this mirror, okay, in this plane. So along the yz plane, what you will see, only this carbon atom is not reflecting, it's at the same position, but this oxygen reflect, and this oxygen also is reflected. So in this case unseparated atom is only one, only this carbon atom, okay. So here we can write one. So the next we will see, the next is regarding our contribution per atom, okay. So contribution per atom, we have already, I have introduced a table here regarding the contribution per atom, okay. Identity will contribute 3, inversion will contribute -3, rotation will contribute 2 cos theta plus 1, reflection will contribute 1, and then improper axis rotation will contribute 2 cos theta minus 1. So here in this case what happened, contribution of E means how much, 3. So here we will write 3. C2, so contribution of Cn, we have how much, 2 cos theta plus 1, no. So it is like 2 cos theta plus 1, that is your Cn, no. So this is the contribution. So here C is how much, C2. C2 means what, 180 degree centigrade, sorry 180 degree. So cos, you can write 180 degree, no, plus 1. So cos 180 degree means -1, so it is your -1 plus 1. So ultimately it is -2 plus 1, so it is -1, no. So here contribution is in all these cases, in all this C2 x, C2y, C2z, all we have -1 contribution, because you can see this contribution table from here, contribution table, you can see here that rotation is given 2 cos theta plus 1 contribution. So and this theta is equal to 180 degree, so cos 180 degree means -1, so -1 into 2 is equal to -2, and -2 plus 1 is equal to -1. So here all these contributions will be -1 in this case. So here also it is -1, and this is also our -1, okay. And inversion, if we see from this contribution table, then we will see that inversion, this one inversion, no, inversion having -3 contributions, so it will be -3 here in inversion, okay. So again we have what, reflection. Reflection, we have just one contribution, okay, contribution is only one. So this is the reflection. So all this reflection will have single contributions, that means 1 1 and then 1. So finally we have just done this operations, okay. Now how from this operation we are going to get the reducible representation. You just see here that reducible representation is nothing, now we have already obtained it, which is represented by this one, no. So you can see 3 into 3, how much, 9. 1 into -1, -1. 1 into -1 again, -1. 3 into -1, we have -3. And 1 into -3, we have again -3. Then 3 into 1, we have 3. 3 into 1, we have 3. 1 into 1, we have 1. So this is ultimately the reducible quantities, okay. So now what we are going to do, from this reducible we are going to find irreducible. So whenever you find irreducible, then there is one formula for irreducible, and that is uh, sorry, irreducible is equal to, so irreducible is given by 1 by h summation of x reducible xi and n, okay. So this is the formula to find the reducible irreducible representation from reducible. So xr means what, character of irreducible. Xr means character of reducible. So xr is nothing but is the character of reducible, and xi means what, xi means character of irreducible. Okay, so it means character of irreducible. And this n means what? Coefficient of your character. Okay, or we can say it, sorry, coefficient of symmetric operation. Symmetric operation. That means this n means what? This n is nothing but, if these are what, this e, c2, I, and we have this one sigma, no, all these have no coefficients here. Okay, but in some cases you will see that there is two or here three. Okay, so this quantity is known as coefficient of this symmetric operation. So since there we have only single coefficients, there is no any 2 3 in this symmetric operations, so this will be 1 only. This n will be our 1. Okay, and this h we have order. And order means what? Order means number of the symmetric operations. How many symmetric operations are there done here? That is the order. Okay, so now we are going to find how. I will show you now very carefully. You have to see. That means how you are going to find the irreducible representation. So we have done already operations, and we have already got the irreducible quantities. That means 9 minus 1 minus 1 minus 3 and 3 3 1. Okay, so these are all what? Reducible characters. So now what you will do first of all, in order to find irreducible, is you will see the character table. Now there I have introduced d2 character table. Okay, so this is the character table of d2h point group. No, so all these characters are what? Irreducible characters. Okay, these symbols are known as Mulliken symbol. You will get in book. Okay, okay, so and these are all what? Irreducible characters. My 1 minus 1, this one, and this character table will be given in your examination. Okay, you don't need to by heart this one, and it is very difficult if you by heart. Okay, so it will be given in your examination. So you just need to have to understand the symmetric operations, how you will derive this reducible representations. Okay, and for this you have to understand the symmetric of the molecules, just like we have done. Okay, so now let us see. Now you see, these are all irreducible. Okay, now you see here that how we are going to find. So this will be irreducible. Az, for az, how you will see az, no, so here az, so let us write irreducible. So we can write it irreducible representation. Okay, so this is our irreducible representation. Okay, so all these are irreducible quantities. So for a1 you see, for sorry az, what you will find here, that az, this formula we will use this one. Okay, this is az. For az, what you will do? 1 by h summation xr xi and then n. This same formula we are going to use. So total you have to do up to how much? b3. Okay, so you will see that h means what? 1. H means 8, so here we will place 8. Okay, then you see here very carefully that summation of xr means, we have already said it is a character of reducible. Character of reducible means what? We have already found the characters of reducible. Okay, so these are what? These are all characters of reducible. So xr, that means what you will see, first character is your for e operation. Okay, uh, wait, okay, so this is the first operation e. So we are first going to see the character, this one e. So you will have to do 9. So this xr is 9, and then into xi means what? Irreducible. Now this xi, from where you will find? This will be from your character table only. Okay, which will be given in your examination. And e operation of az, we have 1, so we will multiply here 1. Okay, and then we have n. N means what? N means what? Coefficient of symmetric operation. So if we see, then we don't have any coefficient in this E. If it is 2 here, then we could have written here, multiplied here 2, but since here is no any coefficient, so you are going to give only 1. Okay, so this is for your E. Now again we will do for C2Z. Okay, C2Z. Now you see here for this C2Z, so here you are going to do plus again, because it is what summation only now. So next is for C2Z, and for C2Z we have already got the reducible representation character, that means -1. So here we will do -1. Okay, and into x irreducible. X irreducible means you have to see from character table. So from character table you will see C2 of AZ is 1. Am I right? So here into 1 into, and you have to see if there is any coefficient, and I have already told you that there is no any single coefficient in E, also in C2Z or in C2Y or in C2X or in I or in anywhere there is no any coefficient. So all these coefficients will be 1. Okay, but if here you find 2, 3, something like that, you have to multiply with this. Okay, so then we will plus. Next character of reducible is -1. No, so here again -1 into, then irreducible character you will see from another, you will see from the character table again. For AgC2 you can see here that it is 1. Ultimately it is all 1 only here. Okay, for Ag, so here it is 1, and you see again the coefficient is there or not. So there is no any coefficient. Okay, so here you don't have any coefficients in C2, so it will also be 1. In this case n will be 1. So similarly for next, this one character, what you will do, you will see this one -3. No, so -3 into this one, x reducible is for -3. You see you have to find this one for all these reducible characters. Okay, and you have to see character table also. So for this -3 we have this one, from character table you see -3 is for what. Actually this is, let me tell you this one. Okay, that this is what, from here you can see 3 into 3, which we have got 9. This is for E. No, and this is for sigma, I mean sorry, C2Z, and this is for your C2Y, and this is for your C2X. This is for inversion, and this is for sigma x, y. No, and this is for your sigma xz, and this is for your sigma yz. Okay, from here you can see 3 into 3 9, which comes from this one E character. Okay, so this is the reducible character for E operation, that means identity operation. 9 is for E, and then C2Z, you can see here that for C2Z 1 into -1 we have -1 here. Okay, C2, and for C2Y we have C2Y is 1 into -1, we will get here again -1. No, so this is actually the multiplication. This reducible representation is from this operation which we have obtained. Okay. So now let us just move back again to our irreducible representation. Now you will see here that it is 9 for identity. Okay, and it is -1 for C2Z, and -1 again for C2Y, and then C2X is equal to how much? C2 is equal to C2X is equal to -3. Okay. -3. So this is -3, then x irreducible what? This one xi irreducible of C2, this one from character table you see again. For AZ we are performing for AZ. No, and then this is what for inversion. Am I right? oh, sorry, it is for uh, this one C2x. C2x. So for C2x character from AZ, and this is your AZ, you see here from character table AZ, C2x is how much? 1. Irreducible character is what? 1. This is the irreducible character, so it is 1. So here we will multiply 1 again into, and then n means what? N means I have already told that in this C2x, does there any coefficient 2, 3 or something else? No, so it is 1 only. No, so here we will just multiply 1. And similarly plus we will do, then we will see again for inversion. Inversion is also minus 3, so here minus 3, reducible character is minus 3. Okay, minus 3 into, then what is xi? Xi from here you will see again for inversion it is also 1. Okay, 1, so here 1 into 1. So again for this sigma xy plane we have 3 into sigma xy plane from character table irreducible character is 1 and no coefficient is there, so it will be 1. So plus again sigma xz. Now this sigma xz is from I mean how much sigma xz is, we have 3 no, so it is 3 here, 3 into, and then irreducible character you will see again from the character table for sigma xz, so it is also 1. So here you will get 1 into, and there, since there is no any coefficient, so it will be 1 only. And lastly for sigma yz character plus 3, oh sorry, it will be 1 into this reducible character is 1 for sigma yz. Now we will see irreducible, this one xi in from character table. So for az sigma yz is 1, so it will be 1 into, and this is the coefficient. So is there any coefficient from our symmetric operation? Is there any coefficient in yz plane? There is no any coefficient in yz plane, so it will be 1 only. Okay, so we will sum it. So after summing this one, what you are going to get is this one, 9 into 1 into 1, it will be 9. Then this is minus 1, 1 into 1, so it will be minus 1. This is minus 1 into minus 1 into 1, so it will be again minus 1. And this is minus 3 into 1 into 1, so it will be minus 3. And then your this is minus 3 into 1 into 1, so it will be minus 3. So this is your plus 3 plus 3 and then 1. So we will cut this 3 and this 3 also cancel, and then from this one we can cut this one. So 9 minus 1 is left. 9 minus 1 is equal to 8. So 8 by 8, how much you will get? 1. So az irreducible representation, irreducible character of az is how much? 1. But you can see it is a very long one. You have to find similarly for b1g, b2g, b3g, au, b1u, b2u and b3u. In similar manner you will have to find. So I will just do it directly, okay, by looking at the character table. So for b1g, you see for b1g how you are going to find the character table. Same formula, that means 1 by 8, and then summation you will have to do summation of what? xr. No, so xr means again this one you take irreducible character 9 into, then you will see xi for b1g, since it is for our b1g, so now we will see all these b1g characters, irreducible characters in our character table. Okay, so here it is 1, so 1 into, is there any coefficient? Is there any coefficient? You will have to see. So there is no any coefficient of e, so it will similarly be 1. So plus, again you will see for next is -1. So -1 into, and you will do this one by so for C2 you can see, for C2 we have 1. So here it is 1 into, no coefficient is there, so it is 1. So same way I will just go on doing, okay, this one by looking at the character table. Same way you can do other, the video will be so much lengthy or else, okay. So uh, you have to do the same way you can do. So how much you are going to get here, so this will be plus. Similarly here it will be plus. So again you will go for -1. So it is -1 into, and you will see it is -1 again from irreducible character, I mean the character table, -1 into, and it will be 1 plus, then you have -3, no, -3, -3 into, -3 means C2x, C2x, no, -3 C2x. So B1G C2x -3, which one? C2x, this one, C2x is also -1, no. So here -1 into 1. Video will be so much lengthy if we write all these multiplications, okay. So what we are going to do, I will just solve this one again. I have written its answers, okay. That means you will get some, this one, okay. Yes, so this will be very lengthy, and then -3 plus, again you have -3 into, we have, for inversion we have 1 into 1 plus 3 into, it will be again 1 into 1 plus 3 into 1 into 1, oh sorry, here -1, and plus 1 into -1 into 1, okay. So here also similarly you will get 1. So same way we have to multiply, and after multiplying all these characters, okay, after multiplying all these, after finding all the irreducible representation for a g, b1g, b2g, b3g, au, b1u, b2u, and b3u, what you are going to get their values. Same way if we want to find the irreducible representation for other characters, we will get the values, okay. So here I am directly writing their values. Actually I have their values now. Here you can see that for b2g we have 1, and b3g it is 0, and then for au you will get 0, for b1u you will get 2, and for b2u you will get 2, and for b3u you will get 2. Same symmetric operation if we perform for b2, b2g, b3g, a1, au, and others, you will get these values, okay. So you have to check these values, you do by yourself and check these values, okay. So now you see next what you will choose. So total irreducible representation are what? AG we have got 1, okay, and B1G we have got, I mean we can write AG here, AG, and then plus B1G plus B2G Then B3G is 0, so we will not write it here. Okay, and AU is equal to 0, so we will not write. So plus, again, you are getting how much here? 2 in case of B1U. It is 2 B1U plus 2 B2U, and what is this one? B, I think, no, BU, B3U, no, sorry, here it will be B3U. So plus B3U is equal to 2. This is also 2, so 2 B3U. So these are the irreducible characters. Okay, so these are the all irreducible characters. Now we got reducible characters and irreducible characters. Now you see how we will find our since we have started with this one, that reducible irreducible representation, and we have to find a vibrational mode. You see here how we will see how we will find a vibrational modes. So next is then how we will find a vibrational modes. You see here, since this is our character table for D2H, which we have followed for carbon dioxide molecule, uh, translational characters. Okay, translational characters, if you want to find, then you will have to check where is XYZ lying. So what you will do, check where is XYZ lying in character table. In character table you will have to check where is XYZ lying. So this is our character table which we have followed for carbon dioxide, so we will check where is XYZ lying. So since it is for a translational motion, okay, so you can see here that XYZ is lying at this B1U, B2U, and B3U. So these are all translational characters. So it is nothing but B1U plus B2U and B3U, B3U. So this will show translational character. Okay, these are all translational character. Now in order to check rotational characters, you will see, you will have to check, where is Rx, Ry, and Rz lying on character table. Okay, on character table. So you will then get its rotational characters. So if you see this one, D2H point groove, you will see that Rx, Ry, and Rz are at B1G, B2G, and B3G. No, so these are the ones that will have rotations. So B1G plus B2G plus B B3G. No, so now what we are going to do next is like we will see vibrational. Okay, so there is one formula again for our vibration. In order to find the vibration, what you will do, vibration, if you want to check, then you will have to do this way. Vibration is equal to total irreducible characters minus translational plus rotational. Okay, so it will give you vibrational characters. Okay, so you can see here irreducible means how much we got. So these were all irreducible characters. This AG, B1G, B2G, 2B1U, 2B2U, and 2B3U we are going to write here. Okay, so here is like AG plus B1G plus B2G plus 2B1U plus 2B2U plus 2B3, you know. So these are all irreducible, this one. So minus you do translational plus rotational. Okay, translational, since they are not, this is of what, U symmetry and this is of G symmetry, so directly we will do is minus. Okay, so translational is minus b1u minus b2u, then we have here minus b3u minus of b1g minus b2g minus b3g. Okay, this one. So how much we are going to get now? So this will be ag plus, you see this b1g and this is plus b1g, this will be cancelled. Similarly b2g will be cancelled. Okay, and this b3g is actually 0, its value is 0. Okay, so b3g value is 0, no, so it's 0 only, that is 0, we will not calculate this one. So finally we have ag plus 2b1u 2b2u and 2b3u minus b1u b2u and b3u, so it will be b1u plus b2u plus b3u b3u. Okay, so these are the four characters you are getting. Okay, vibrational, these are the four characters. Okay, one is ag, b1u, b2u and b3u. So this particular one is Raman active. Okay, Raman active, and the other three is IR active. IR active. Okay, why I'm saying it is Raman active? Because uh, if you see the diagram, this one character table, then this ag, there is quadratic equation, no, so if there is quadratic equation in this character, that will character will be Raman active. Okay, and if you see b1u b2u and b3u, b1u b2u b3u, this is xyz is present there in b1u b2u b3u, xyz is present, so those are translational, they will exhibit translational motion, and those characters are what, IR active. Okay, so carbon dioxide have, so CO2 have 4 modes of vibration. Okay, so as we know, the 4 modes of vibration of carbon dioxide, they are, one is this one, no, uh, stretching vibration it will have, which is symmetric stretching. Okay, and also it have asymmetric stretching, asymmetric stretching, no, and we have this one, bending mode of vibration. Okay, one is out of the plane, this is out of the plane, bending. Okay, there are two bending modes, this is also bending mode of carbon dioxide. uh, this will be inside the plane. Okay, this is also bending. Okay, so this symmetric mode is your Raman active. Okay, and rest asymmetric stretching, bending, and this bending is also IR active. Okay, sorry, so these are IR active. So you can see this is the way how you can find vibrational modes from the this one, and from the irreducible and irreducible character table. Okay, hope you like it. So if you like it, then subscribe my video. Okay, thank you friends.